Okay, so then let's start with the lecture. So last lecture we spoke about agnostic setting. Come in, please. Now we will continue with agnostic setting. Well, till the end of the course, we will speak about agnostic setting. Last lecture we proved some nice bound. We proved there is bound that uses VC dimension, and there is kind of a message that says that if you want to fit a model and you're worried about overfitting, then let's try to have small VC dimension, because overfitting term was proportional to square root of VC dimension divided by how many training points you have. VC dimension is proportional to the number of parameters that you're fitting. And so there is a nice message. Unfortunately, this message does not correspond to practice. So in machine learning, they say, oh, the bigger your neural net, the better. So the more parameters you fit, the better you're working. And so why does this theory give opposite like conclusions or like opposite suggestions? So the issue is that this theory works for all input-output distributions. And now we will give a new theory, and we can apply some margin assumption, and then we can obtain like some similar conclusions. That we will obtain a new objective. We have a different overfitting term, and it goes down with the margin size. And the more parameters we have, the bigger we can make the margin. And that's why the overfitting term becomes smaller with more parameters. But all of this theory, it's like not working perfectly. There are many strange things, strange data sets on which these risk bounds make no sense. And there is a lot that hopefully soon will be discovered about this. Okay, so the previous function, so in the previous lesson, we measured the capacity of a set of classifiers by the growth function. Now we will use Rademacher complexity. And so that's the main goal of this lecture, introduce Rademacher complexity. Then we will see that it has many nice linearity properties, and we will prove two important theorems called symmetrization theorem and contraction theorem. Contraction theorem will be for the seminar. Okay. So let us say, what is this Rademacher complexity? Rademacher complexity is the average correlation of a classifier with randomly generated labels. So that's the definition in words. So let us write it step by step. Well, first we need something. So Rademacher, well, you know what? I will first write the most important risk bound of this lecture. And then I will define everything a bit later. Because the reason is that we will use very general definitions and make the theory a bit abstract. Okay, so what we will have, a corollary of the symmetrization theorem will be the following. So if we have a set of functions, a set of classifiers H, they map from X to the labels -1, +1. Is this sharp? Is this readable? Oh, it's even sharp. But it's you cannot read it because it's, I need to flip the screen, I guess. Let us go to video settings. Okay, so we have a set H of classifiers. We use labels -1 and +1. And we will prove that so for every measure, we have this, and then with probability 1 minus delta over a training set S generated from Pn, all classifiers in H satisfy a risk of F is bounded by fraction of misclassified points on the training set S plus 2 plus Rademacher complexity. This is the square R, this funny R is a notation P and N of the class F plus something small, a term that you will recognize. It is 2n divided by ln1 over delta. So with high probability, the risk is close to the error on the training set. And so that's the most important risk bound for this lecture. But now I need to tell you what is this mysterious Rademacher complexity. Sorry, and it's the empirical risk, fraction of misclassified points, and here is the Rademacher. Okay, so that will be our goal. So it's a very nice interpretation. So here is correlation of a classifier with randomly generated labels. So the error on the training set plus correlation with randomly generated labels will be essentially our risk bound, because this term is always small. We know that this is a small constant and the data set is usually a few hundreds. So this goes down, this is usually much smaller than this thing. It's a bit sad because of the square root.
This theorem is independent from the theorem from the previous.
Yeah, the proof is independent.
And the result also independent.
No, I will explain that with this result, we can a little bit improve the previous result. But a proof is very abstract. So that's why I postponed till very late. Now you're ready for some, like, you know, the ideas well, and so we can speak about it. Okay, so now let us speak about what is this Rademacher complexity. So first, it comes in two variants called empirical Rademacher complexity and average Rademacher complexity. So that's the average one. We start with empirical Rademacher complexity. So it is denoted like this, and here, okay, sorry, that's our result. Now, first, I need to define it more generally, because next lecture I will speak about regression. So now we can no longer postpone it. And so I will use a class of functions that's denoted F. It maps inputs. So this is a set of functions from X to real numbers. And the letters F and G will always be such sets, and there will always be non-empty. Now there is another very annoying thing. I need to replace the set X by something more general. So I will use Z. And in all applications, Z will be either X or X times Y. So I need to use a different letter. Okay, and now let us define empirical Rademacher complexity. And F will be the set of functions from this C to R. Sorry for this. G is also such a set. F and G, like H, always assumed to be non-empty. So I'm not going to repeat it all the time. Okay. Finally, the definition. So empirical Rademacher complexity of the letters. So here we have curly Z, which is equal to curly X or Y. Z is a list of training points. The Zn is an element of curly Z to the power n. And when we have such a training set, we define empirical Rademacher complexity of the class F as, and here I said expected value of correlation with random labels. So what are the random labels? They are written as sigma. It's called Rademacher variable. Sigma is random element in -1 plus 1 to the power n. So sigma is a random element in this class. Rademacher complexity is expected value of best correlation. So what's the correlation? F is an element from our class F, and the correlation is just sigma n F C n. And so note,
If it's uniform distribution,
yes, sigma is uniformly random in this set. And so here is a definition, and it's the best correlation. So we take the supremum over F in our set F. So Rademacher complexity is average correlation with a function in F, with the best function in F for random labels. So sigma 1 is a Rademacher variable that takes values -1 and +1 with probability 1/2. Okay, so now let us look to some easy properties. So imagine that F is a subset of G. So what about monotonicity? Rademacher complexity of F, is it larger or smaller than G? Yeah, Rademacher complexity of F can only be smaller because just a supremum. Okay, and then let's take look to the function of F. So we said that F is smaller. So what if F contains just only one function? So what's the value of this empirical Rademacher complexity? It is. Yeah. So what happens if F contains only one function? So in this case, sum of absolute values of F is 0. Oh, somebody is saying something. Okay, I hear something, but I think it's yeah, that somebody needs to turn off. I can, oh no, I cannot ask to mute. Okay, it stopped. Yes, exactly. So let us see why it's 0. So if F contains only one function and it's a function F, then I can just delete the supremum, right? And so we don't need these brackets. And then let us look at the first term. So Z is just a list that's fixed, F of Z is fixed, and we take expectation over sigma 1. Sigma 1 is -1 and +1 with equal probability. So expectation over sigma. So when we look to expectation over sigma 1 over a random variable, it's equal to 0. So the first term will be equal to 0, and for the same reason, all other terms also 0. Okay, next example. Imagine that H is a set of all classifiers from from some set X to -1 and +1. So what will be the empirical Rademacher complex?
n multiplied to the power of n.
Yeah, sorry for the definition. I forgot to scale. You need to scale by 1 over n, the size of this set G, of this list G. So there is
2 to the power of n.
Z of H is equal to 2 to the power of n. Okay, what do the other things? Are there other values? it's a bit too much. I think you should carefully check supreme. Yeah, you got the right answer, but yeah, you took the sum instead of expectation. So it is 1. So do you see why it is 1? So for the others, somebody else can explain why do these 2 students say 1? So here we have the definition, the supreme one.
Just all functions. The one on.
So if we have all, oh, sorry, I forgot to say something. It's not true. If all the z's are equal to each other, then it's not 1. So I need an additional assumption. Assume that all elements are different in Z. Okay, and now we can say that's equal to 1. Because all the Z's are different, we have all the functions, and I was wrong. So you can indeed think when you see Z that's equal to X, but at some point we need to set it to X times Y. It will be later. Okay. So if all elements are different, that means we can we have all different inputs, and so we can choose a function for which sigma I is equal to f of zi. We choose such a function, and so here we will have the value n, and when we scale by n, we have the value 1 for every choice of sigma. So it was clear. Okay, what else do I need to? What else do I need to tell? It's happening here in my papers. That's done. I've already said this. Okay, I think I've said everything. So what we conclude, when H is just a general set with of classifiers with labels -1 and +1, then we conclude that R of H is between 0 and 1. And so if H contains just one function, then it is 0. It's still visible on the board, yes. If we have all functions, it's equal to 1, and for general sets, it's in between. So it measures how rich is H. So recall that it's monotone. The more functions we have, the bigger it comes. Maximum value is 1. Okay. Now I did something stupid. I had to give 2 parts. There were 2 parts in the lecture. I started to speak about the second part. And now I need to change my plan. So that is okay. So let us speak a bit more about basic properties, and then I will jump to the first lecture for the first part of the lecture. Okay, so so one of the nice things about Rademacher complexity, it can be used when you build for complex classifiers that are built from small parts, like a neural net is built from small parts. It has linearity properties, and that's good for linear regression. So let us look to some simple linearity problems. So for example, imagine that we create a new class. So we start from a class F, and we create a new class by multiplying all classifiers in F by some constant A, for example. So what is, let us denote A times F for a real number A. Let's say A is at least 0. this is just given by the set of all functions that map z to a times f of z for f in the class curly f. What can we say about Rademacher complexity of a of f? So yeah, indeed. Oh, sorry, I should write curly f here. Okay. Imagine that we have two classes, f and g, and we look at the class f g obtained by adding one function from f and one function from g. What happened to the Rademacher complexity of the sum? What is Rademacher complexity of f plus g? And I will write a formal definition. All functions that map. Well, I can just write f plus g. So what is it? So the maximum is useful when you look at the union. It will be for the seminar, you will think about it. Yeah, so here we just add up the functions. So that means when we look to the supremo of all sums of two functions, yeah, we can just write it as two sums and pick the best function independently. So this is Rademacher complexity of f plus Rademacher complexity of g. And so that's do in a neural network. You add up the weights that arrive in all the input wires of the neuron. Oh, I forgot some simple one. What happens? What is the Rademacher complexity? Z of f plus a constant. So A is any real constant. So that means that yeah, exactly. So if we add the constant to all functions, then this constant will appear here. Then we have something similar. And now an important one. Here is because so what we do is we take the constant does not appear in the supremo. So let us just take about the plus a that appears in the first term. So we can bring it in front of the supremo, and we have sigma 1 times a constant, and so it disappears. Okay. Now let us multiply by a function. So let us consider a fixed function h. H is a fixed function that maps to -1 and +1. So h maps z to -1 and +1. And what if we multiply the class by h? H maps z to -1 +1. So what can we say about the Rademacher complexity of h times f? Yeah, so what we're doing here, we're multiplying by -1 or not doing anything. So when z is equal to +1, we don't do anything. If z is equal to -1, some points get multiplied by -1. Some of the terms get negative. And so how does this affect Rademacher complexity?
Maybe not the same.
Nothing changes. This equality still holds. And why is it? So what happens? So just look, sigma 1 is distributed in -1 and +1. So what minus sigma 1 has same distribution. It is -1 and +1 with 1/2. So this is the same as just renaming sigma 1. So it doesn't change if we multiply by all the functions by some fixed labels. Okay, and this is an important observation when we prove symmetrization theorem. So the Rademacher complex variables are symmetric. Okay, and yes, that's already a lot of basic properties. There is one more. Well, there is. Okay, we can now combine all linearity properties. So imagine we have a few classes, F1 till Fk, and we take a linear combination of these classes. So that A1 till Ak be real numbers and consider classes F1 till Fk. Let us now look to the Rademacher complexity of linear combination. A1 F1 plus Ak Fk. So this is equal to, yeah. Looks like my questions are too easy for you. F1 plus Ak. There is a small error in what I write now. Can you see it? So it's almost correct. Well, I wrote that is an R, so coefficients can be negative. So if we the Rademacher complexity of -f is equal to Rademacher complexity of f. Again, by flipping the values. So we can fix it. We just have to put absolute values in this coefficient. And now it's correct. And now there is a small lemma that says that that is defined convolution of a function. I will use a simplified definition, otherwise I have to write too much. Let us say the convolution of, where we take two functions in f. So that is equal to a f z plus 1 minus a f tilde of z. Where f tilde are in f, and a is between 0 and 1. Okay, so I claim that Rademacher complexity of conv2 equals Rademacher complexity. Why is it true?
Because we have supremum and supremum on compact. Okay.
So a difficult word. So there is, yeah, So what's happening here? We indeed need to focus to supremum. Let us use the word maximum. So maximum over A between 0 and 1. So of this expression. So we have some function of, so here we have some expression E of F. And we will multiply by A, and we will multiply by 1 minus 1 on F tilde. So when we look to this supremum, so we apply this supremum on functions that are convolutions of two functions in F. So of this linear combination. And what can we do? All terms that contain F we can bring together, and all terms that contain F tilde we also bring together. That's the plan. And then we get an expression of this form. All terms containing F, all terms containing F tilde. And here is this correlation. And here we have the supremum over F and F tilde. And then, and so on. But let us now focus on this part here. We take the maximum over A of these two numbers. They're just real numbers. And we know that this maximum will be on the extreme points, either A equals 0 if this one is larger, or A equals 1 if this thing is larger. And if they're equal, it doesn't matter which A we take. So that means that when we look at this maximum, so when we look over supremum over F and F tilde, and then this maximum, we can just replace it by just the supremum over a single function of the expression of F. So this will be the same. So when we look at the supremums, then this thing equals this thing. Yeah, my marker is going bad. So it's not clear, right? For some it's clear. Not clear? Okay, so here let us look to this supremum. Now we apply it to functions that are in convolution 2. Okay, so that means we have to look to functions of this form. So every F we have to replace by this expression. Afterwards, okay, so when we have convolution, we have two functions and we have these expressions. And expression we get here, we can write in this form. How do we get it? So we collect everything with F here and everything with F tilde here. So it will be this sum with F tilde. And then we can bring the A's in the front. Everything with F has an A in the front. One might has this thing in the front. Okay, and now we can look to this expression. We take the maximum for A. If this one is bigger, we set A equal to 1, it will be the maximum because it's a linear function of A. If this one is bigger, A is 0, is the maximum. So that means we can basically drop this A coefficient and just look to the maximum of these two. But then we just take the supremum by taking 2 is the supremum of 1. Okay. So that's for convolutions. Will be important for AdaBoost. When we apply RISC-bound to AdaBoost, AdaBoost takes a linear combination with positive coefficient. After scaling, it computes convolution of the base class. Okay, that's a lot of talk about the basic properties. So now we are already very experienced in dealing with Rademacher complexity. So now I need to explain, we want to prove this corollary. is from a more general theorem. But for this, we cannot use Chernoff bound. So this reminds you of Chernoff bound, right? It's like if you set the expression exponent -2 epsilon squared n equal to delta, and we solve for epsilon, we get this thing. We've seen it many times in risk-bound last lecture. So, but Chernoff bound is not able to get this result. We need a stronger version of the, we will need to use bounded difference inequality. And so now I will explain what is this bounded difference inequality. I will keep the corollary because we will need to prove it. The definition I will delete to have more space. Okay. So this is chapter 10 of lecture notes. But I need a better marker because I'm afraid in Zoom. So there will be 5 minutes break while I get a new marker. And I will get something to clean the board as well. Very fast. They were in my pocket. And does someone have handkerchiefs? There is. Ah, cool. Okay, can you give it to me? Thank you. Okay, bounded difference inequality. So Chernoff bound, let us look at the sum of independent variables. Now we will look to just any function applied to all the of n different variables. And we will say that the same bound holds, provided this function depends not too much on a single variable. So if we have a function that kind of smoothly depends on each variable, then we can apply Chernoff bound just on the outcome of these variables. We only require that variables are independent. And even this is too much. Azuma's inequality is even more general. But then I need to tell you what is martingale and so on, and I will not do this in this course. I will just tell you what we need to get the risk bound. Okay.
So people with this auditor already know.
Ah, okay. You're smarter than me. No, I also know. I forget all the time because I don't use it much, but sometimes it's useful. Okay. Yes. So what is so function should not depend too much on each variable. This is translated to bounded difference condition. So bounded difference condition means that if you fix all variables and you change one of the variables, then the function value changes at most, and we will say 1, changes at most 1, just because then we have fewer letters. So this bounded difference condition. Okay, so let me write the theorem directly. Wow, it almost hurts in my eyes to finally have a good marker. So assume phi satisfies. So assume that for all, let us fix x1, x2, and variables, and let us for all I smaller than n, so we will have n variables. We will modify the ith variable, and so we need to fix all variables and a new value for the ith variable, and we assume that absolute value of phi x1, xi, xn minus phi, and now the same function with the ith variable modified and we require that this is smaller than 1. And this should hold for all ways to choose I in the variables and xi on them. Okay. Then let us have x independent and independent variables. Okay, and they are all in x, in subset x. And then let us define the random variable phi. It is equal to the function phi applied to all these variables. And then we have this general bound that applies. So the probability that phi is bigger than expected value of phi plus epsilon times n is smaller than exponent minus epsilon squared n. So this is bounded difference inequality. So that's nice theorem. So very famous theorem, and it's many applications for theoretical computer science guy. Whenever you use randomized algorithms, you have some chance to need this inequality. Okay, so how do we get the channel bound from this? So for this, we will choose this function phi.
That's only the one by two.
Yeah. Well, we don't need to divide by n because I have here. Yeah. So phi x1 plus sorry. Okay. What else do I need to say of trivial observations? Let us have some applications. So there's quite simple applications. So let's have two applications in computer science. So you know that processor. So there is a problem of bin packing. So you get a series of objects that get certain sizes, and you need to divide them over bins of size 1. So the input of the bin packing problem is a list of fractions: 1/4, 1/3, 1/2, 3/4, 4/5. And some number, and you want to pack, so these are 5 objects of these sizes. You want to pack them in bins of size 1. So what's the minimal number of bins you can use for this? In this case, you can use 3 bins because you can combine this and this. You can combine this and this in 1 bin, and then the last bin is not full, and the second bin is also not full. Okay, and so it's NP-hard problem. So if you get a sequence of objects, you're not going to find an algorithm that computes efficiently in all cases what is the optimal allocation of bins. But something funny is that whenever you have a good algorithm for a certain application and the objects are generated independently, then you can know for sure that the number of bins is always very close to its expected value. So do you see why it's true? So here the function phi is very difficult function, NP-hard to compute, to evaluate in general, but we know that its expected value is very close. So when we set epsilon equal to 1 over square root n, this becomes quite, we can make this rather small. And so we see that deviations will be at most square root n when we have to pack n objects. And so why is the bounded difference condition satisfied? So here phi represents minimal number of bins to pack the objects.
If we have
it's obvious. Yeah, it's obvious. If we change one object, like for example this object, then minimal number of bins can either decrease 1 or increase 1. So if we change one object, the ith object, okay, we of course we assume that all objects have size at most one, and no negative sizes. So if we change one bin, then phi can change by at most one, increase or decrease by at most one. Actually, here you don't need absolute values, because you can always flip xi and xit. Okay. Yes. Second is longest common subsequence. So here it's needed in bioinformatics. So there are two protein sequences, B1, B2, Bn, and I want to know whether they come from the same piece of DNA of the same animal. And so they compute longest common subsequence. Do you know the problem? Do I need to give an example? So, for example, when we look to 0, 1, 1, 0, 0. Yeah. So longest common subsequence is probably by selecting this and this. And so here, so there are two equal sequences. I think it's the longest one. Okay, and so what happens if you need to evaluate? So phi is the length of the longest subsequences of AB, of these two strings. So what if you generate bit strings uniformly randomly? So then it's open question, what is expected value? So phi longest subsequence, what is this expected value? People know that it's at least linear in the length of the sequences. So if this is length n, this phi will be at least n. But remarkably, this longest common subsequence is close to its expected value. So it's open question. So people have run simulations and they found that there is something, I think, times n is the expected value of the longest common subsequence. So it seems to converge to this value, but nobody can prove it. So if you want to write a paper, then you can try it. Okay, so that's two examples. I also said previous lecture, we had a problem with a bag of balls. And the question is that what's the probability if we randomly split, so we have a bag of objects, we randomly split it in two halves, what's the probability that one half has much more marked objects than the other half? So we had a lemma last lecture. So let me make, so here is a bag with objects, and some of them are marked. L marked objects, a random half, and let K be number of marked objects in one half. Yeah, you know it very well from homework, I guess. So K marked object in one half, and then there was a lemma. So probability that K over L is smaller than 1/2 minus alpha is smaller than e to the power minus 2 K, sorry, 2 alpha else alpha squared. Okay, let us replace alpha by epsilon. So there was some reason to use another.
That was the relation, but without proof.
Yeah, we skipped the proof. I will say I will do it next time because it's a nice application of this. Now it's not direct application. We have to think a little bit. What would be the x1, x2, and so on. So I will tell it now. So here we have a bunch of objects. We need to take random half. Let's do it in specific way. So let us make a line, and so let us reserve places for all the objects. And so at some point, there is the half of the number of objects. And then let us go and overall objects in certain order. And let us put them on the random place in the line. So number one will be placed in a random place. Number 2 will go in another place. Maybe here. 3. Okay, let us now define random variable xi. Xi will be will encode the position where the ith object goes. But so xi v equals v. V is an integer. So v is smaller than. So v will be if imagine we have n objects. No, not n. We have m objects. Okay, so v will be smaller than m minus I. It will denote the index of the place that's free. For example, if x4 equals 5, that means that the fourth object goes to the fifth free place. So 1, 2, 3, 4, 5. And so that means we place 4 here. And in this way, we can generate independent variables. So note that if we use as variables the positions, then they're not independent. If all the positions in the beginning are filled, then the next random variable will be higher with certain probability. So those who know Azuma's inequality, they know for them it's no problem, this restriction, if we do it in this way. But we don't have the general version. So we will set xi equal v, denote the index of the place where we place the index of the free place where the object goes. And now all our variables x1 till xn are independent. Okay, and here we can do this using any order of the object. So let us first place the marked objects and then don't care about the other objects. So now I can tell you how we get this result from this theorem, or maybe you can already tell me what is phi. Phi will be, yeah, phi will be number of marked objects in the left and one side, yeah, in the first side. So now we want to apply this theorem. Okay. So now we only care about the first L variable. So we can set n equal to L. Okay. We have to check this inequality. If we change the position of one marked object, how much can phi change? It's indeed 1. And so if we change, here is a marked object. If we change that variable, it means that maybe we put it here. If the object is, so there's a marked object that goes here, that means at most 1 can be less here. But if we are lucky, so all the others, they move to the right. So when we're lucky and this one is a marked one, it will go here and nothing changes. Or opposite, if the marked object is here, we might bring it here and then it increases by 1. So this condition is satisfied. And this lemma is proven that we had. Because 1/2 is expected number of marked objects in the first half.
Why do we need to put this x, y? Why we can't also say that our I is just number of objects in the first half, and that can decrease, well, can change only by 1, and why we...
Well, we need variables to apply the theorem. We need independent variables.
Mm-hmm.
But okay, those who already know Azuma's inequality, they can get. Yeah. But then I will tell you, if you learn it later, you can think about, oh, actually, this is easy inequality. By the way, this lemma is wrong in many books. So that they say that this follows from Hövding inequality. But it's not true because variables are not independent. Okay.
So here we just say basically that our phi depends on this xi and that's only why we need.
Yeah, we need a special construction to make them independent. So as I said, if it's just xi equals v, means the ith bulk goes to position v, they're no longer independent. Because after we filled the first half, then with probability 1, yeah. Okay. So yes, that's cool. So there was another one, a really cool result, maximal inequality, and we will also need it. So now the lecture is a bit boring because we do all technical things after each other and then prove the main interesting result. But okay, it's my fault. I was not paying it. I was thinking too much about all these nice proofs and I started in the wrong place, or maybe the right place, depending. One can discuss whether one should first have all technical things and then the proof. Okay, so maximal inequality. We will only need it twice in this lecture, maybe one time in next lecture. So once in the lecture now and once in the seminar. And then I think. So the maximal inequality gives a bound on the expected value of the maximum of several variables. And these variables may be dependent. So it's kind of a funny thing. If people look a bit tired, maybe. Okay, but still it's just 5 minutes and then I have 15 minutes for this. Okay, might work, but we also have quiz. Okay, let's try to say it fast. So this theorem considers a matrix of random variables. All random variables are centered and they are in an interval -1 + 1. And the question is, we will look to the sum of the rows. What's the maximal sum of a row? And the claim is that expected value of the maximal sum of a row, x I1 plus x in, is bounded by, and here comes a formula, 2n ln d, where d is the number of rows. So we have x, random variable in -1, 1 to the power d times n. So we have a random matrix with d rows and columns. And then we have some more assumptions. Okay, so I write the assumptions here. This is it's not a nice arrangement on the board. The second is all variables are centered, xij equal to 0. The third assumption says that columns are independent. So in every row, the variables are independent. So for all I smaller than d, xi1, xin are independent. Okay, and if these three assumptions are satisfied, then this inequality holds. That's maximal inequality. And so there are funny things you can do. So it's very strange. I used this many times in research, but each time the proof was ready, I simplify it and maximal inequality falls out. So just having Chernoff was enough. Okay, but the proof is really interesting of this inequality. So let me quickly go over it. So it's reasonably short proof. So let us write BA as the sum BA xi1 plus xi. And so we have to look at the maximum of V1, VD, the sum of the rows. And we will use softmax upper bound, which is also used a lot. So this proof is good exercise because many important things that will be reused later, and also for homework, it will help. So softmax upper bound is it's defined for some s strictly bigger than 0, a real number. You can choose it whatever we want, and we will choose it later in some optimal way. This ln of sum e to the power s vi I equal to 1 to d. So this is upper bound for the maximum, real softmax upper bound. It has several names. Log sum x for yeah. Okay. So now we want to take expectation on both sides and get an upper bound for it. Okay, now the next step is to bring expectation inside the logarithm. And we can do it because of with inequality. Yeah. So ln is logarithm. So when we look at the average, we go up in value. So this is bounded by 1 over s ln sum I equal 1 to d of expected value of d to the power s g I. Okay, and when you see this, we want an upper bound for this. What do you think of? So let us take this apart. E to the power s I. Well, let us first expand it. So vi, maybe we should use. Yeah, so let us first expand it, and then I will ask again what you think about. So these are independent variables. So that's this assumption. So that means this this exponent is a product of e to the power s x I 1 and so on, e to the power x I n. Okay, now xi1 is a variable in this interval, bounded variable, and we need to bound the exponent of it. So what are we going to use? We've used it already twice. You will use it again to prove bounded difference inequality as homework task. That, by the way, always everyone has right, so it's an easy exercise. It's easy homework. Okay, we will use having in lemma, having inequality to bound exponent of sxi of s times a variable. But the variable usually it's in 0, 1. So and then we have this 1/8 of s squared, exponent of 1/8 of s squared. But now we have a wider interval. And so when the interval is of size b instead of size 1, then we have to divide by 1 over b. So we have to scale this s squared by 1 over b squared. So each term is bounded by e to the power s times expected value of xi1 plus 1/2 s squared. And then similar for the other terms. And what do we know about expected value of xi1? Is 0, yeah, because of this assumption. So this falls off this term. And so all the bounds are now the same. They're all equal to 1/2 s squared. So this is equal to e to the power n over 2 s squared. So this is for what is in this sum. So what have we proven? It is bounded by 1 over s ln of d times e to the power n over 2 s squared. Now we can simplify this a little bit. So let us write ln of the product as a sum. So we have ln d over s plus then ln of exponent cancels. So what we get is an s over 2. Right? So that's just equality, just working out. Now we will select s so that this is minimal. And it can be calculated that it's minimal when the both terms are equal. And so s is equal to square root ln d. To n, I think. No, the 2 is here at the top. Ln d over n. Okay, and if we substitute this value for s, we have precisely this bound. So this maximal inequality. Okay. So now let's do a small application. Oh, time is not going well. Okay, one application. So imagine that you are on a line, and you randomly, like they say, drunken walk. A guy randomly goes one step right or one step left with probability 1/2. And then the question is, what is expected value of his distance from origin after making n random steps? Yeah, it's a cone. So we can solve it with this maximal inequality. Okay, so here we will, so first we have to look to the absolute value of the sum of all his steps. So the step is +1 or -1, depending whether he goes right or left. Absolute value of r is maximum of -r and +r, right? So here we will apply it, and we will have matrix with 2 rows. The positive of all his steps and the negative of all his steps. So we say that x1 I equals 1 if he goes to the right, and x2I equals -1 if he goes to the right, and vice versa with the opposite signs when he goes to the left. So we have 2 rows, d equals 2, and so in this example, we get an upper bound for expected value of his distance from origin. So it is bounded by square root 2n ln 2, because d is number of rows. So in this, I checked it, it's smaller than 1.2 square root n, so it's very close to square root n. So that's the upper. I don't know what is, there is exact value, you can compute it. I once did exercise a long time ago, but I don't remember what's the value. Okay, but this is example. So now you know maximal inequality. It's important for the quiz and seminar. And now our remaining goal is to prove this corollary. So we will not get there, but we will do half of the proof, up to 1 lemma. This lemma I will tell you next time. Okay. So we will get this from a more general theorem. So let G be a class of functions. G set of functions from X to real interval 0, 1. Okay. So G is a class. And then I claim that now we have the same thing. When we generate a random training set with probability 1 minus delta over Z and B to the n, all G and capital G satisfied. Expected value of G and bounded by, and then the empirical value of G over the set Z. So this 1 over n, sum over G of Z. So here we write Z as Z1 till Zn. So, okay, let me write it. We will have 2 times Rademacher complexity Pn G plus and then the square root term. That's the symmetrization theorem. So note that here is a 2 and here is no 2. It's not a mistake. Okay, so first task to prove this theorem. And this theorem follows from this using a lemma. And today I cannot prove it, but the lemma says that First, I need to define a special function. There was a student, he always called it outlier function. And so I don't know whether, I think I'm always thinking whether it's a good name or not. This outlier function is the difference between this and this side. So the maximal difference between this and this side for a function G and the class G. So this equal to the maximum of the left-hand side. So here with the expected value, I just mean that we take a test point according to P minus 1 over n, sum I equal to 1 to n G C. And the lemma says that the expected value of phi of Z is at most 2 times this term, 2 times the Radimax complexity. It's not over function. Yeah, maximum over G and maybe better. Yeah, sorry. Yeah, in this course, you can always think when you see supremum, it's maximum. It's allowed, I will never subtract points. But very serious people, they don't like this. And then you can always adapt a proof that when you see supremum, you take a function G, your epsilon close to the optimal value, and then you do the proof with this epsilon inside, and in the end, you take the limit. It's always solvable. But you don't need to write this because it's a routine thing and it's very boring. It makes things complicated. So the lemma says that for random set Z, this is bounded by 2 times Rademacher complexity and P of the class G. So imagine that we believe the lemma. Do you see how we can finish the proof? So how do we prove this? It's consequence after we get this lemma. It's consequence.
But we don't know the definition and the mark complexity. Right?
Okay. It's expected value over Z. Sorry. Sorry, here it should be without head. It's my mistake. And so that's the same term here. So now you know everything, but it's just expected value for a random Z of size n of the empirical Rademacher complexity. So that's the definition. So the definition is only used inside the lemma, inside the proof of the lemma. Okay, so how do we get this from bounded difference inequality? So the function phi already has clear candidate, right? So we have a different task. We need to prove that phi satisfies the bounded difference condition. So Z is a set of length n. So we need to convince us that if we change one input in Z, that phi of Z changes by at most 1. This is consequence of triangle inequality for suprema. So let us say what we have. We have phi of Z minus phi of Z tilde. Z tilde is just Z with 1 point changed. And we need to prove that this is smaller than 1. But this is of the form, so this difference is just supremum over G of some expression E of G minus supremum, let's change the variable, oh no, needed, E tilde of G, so that there's a different expression. And I claim that this is bounded by supremum of over G of the difference of these expressions, EG minus EG tilde. So people, can you see this at home? And just okay, I rewrite it here. So this is bounded by the supremum of the difference of the expression. So this is just bounded triangle inequality for suprema. Right, so you can say that this is one supremum, this is another one, you put it on the other side to have triangle inequality for suprema. So after you believe this, we have to check these expressions. So what are these expressions? So that's just what is written here. Okay, so in the beginning, first we have a constant that does not depend on, something that does not depend on Z. So we have to look to the difference of these expressions. Here we have Z, here we have Z tilde. Now let us look. This, what is here, is E of G. And we see that, so E, it's a function of Z. This does not depend on Z or Z tilde. So this thing cancels. So this supremum is just the maximal difference of this sum, where we change 1 point. Okay, and I made a mistake. It's better to use this scaling here. And now it makes sense. So this thing doesn't matter for us. And here in this sum, we change 1 point. So it means that this difference when we change 1 point, this difference will be at most 1 because we used functions that are that have values in 0, 1. So here, when we evaluate the sum, EG minus EG tilde, it is precisely equal to G of Z I minus G of, it's again not visible for people at home. So G minus EG tilde, this equal to G of Zi minus G of Zi tilde. And so this is bounded by 1. And so this bounded difference condition is satisfied. So you can, of course, let E and let Zi. So we don't, to prove it, it's enough if we prove this, as I've already said. Okay, so this condition is satisfied. Then we look at independently generated random Z's. So this is true, all fine. And then we can apply this inequality. So what do we get? So let us set this equal to delta. So then we have that with probability 1 minus this exponent, this inequality holds when we replace this by epsilon. But when we set this equal to delta and we solve for epsilon, we get the square root. We already did it last lecture, but then for like estimating for a single function and for finite sets and so on. So we see that this directly implies this. Okay, so what do we, sorry, we get something different. Here we have expected value of pi. So when we apply it, we have this inequality. Pi is bigger than expected value plus epsilon times n. Okay, so sorry, let us be precise. Let us multiply everything by n, 2n. And here is a mistake in my lemma. Okay. So what do we have here? We have moved it to the other side. Let's draw the complex notation. That's what we have proven. So by the lemma, we have something here that's an upper bound for the expected value of pi. That's, so we look to the worst case G for this quality, the supremum is worst case. So if it holds for the worst case, then it holds for all G. Here is expected value of pi. So pi bigger than expected value of pi plus epsilon n. Here is epsilon n, expected value plus epsilon n. This event has probability at most 1 minus delta, and delta is this thing. So that's the proof. And then next lecture, I will prove this lemma, which is also technical, and it's very nice. It will again be like cross-validation bound. We will estimate, we will estimate this expected value. This value we will expect using a test set and then use symmetrization. Okay, so that's more than enough. There is still a quiz left, but maybe I have an idea. We can do the quiz during the seminar because I need to either show it or write it on the board, but it will take a few minutes. And then
We can have burn 5 minutes.
yeah. And also I was too late to set up graders so they can submit by email. Then it's easier for me to bring. Okay, so let's have 20 minutes of break and then start the seminar with the quiz. So, yeah.
First, I was on the first place, but in the table,
Still, your mark is not there, so I did something wrong. So I guess some other student is lucky. So let's fix it.
those you said that for one mistake it will be full
Ah.
score, and for the two mistakes it will be half score.
Half score. Sorry.
Not zero.
Oh, sorry. Okay. Oh, I forgot about two mistakes. Grades. So you are okay. And how much did you have?
2.5. No, first with two mistakes. And
Yeah.
other two.
Okay. So
Maybe it's
maybe I lost your paper because it was in my bag and yeah.
maybe. Also, you said that on the you will tell us how in homework there was a task, this one,
Yeah.
and there was a problem with independence,
Yeah.
and we should fix it like.
Yeah. I need to tell you. Okay.
Some students have another lesson right now.
Okay.
So they need to do quiz fast.
Okay. I will, you know what? I will leave it open till tomorrow. It's okay? Yeah. Then, and you need to email the answers. Yeah. Okay. Yeah, I was too slow in the lecture.
So you will tell you next time.
Yeah, because now there is no time. I mean, yeah. Well, actually, the answer is very short. If you can, so there are a bunch of points in this. So you have the set of k cube, k closest neighbors. When you condition on all the length of the k points, then x's are independent. So what are you doing? So you generate a big set, and then you look to the k closest points. So to make the selection, you only look at the lengths and not the points themselves.
Yes. I just remember
Yeah.
my own solution, and I don't think that I look at points. I sorted distances and called the x1,
Yeah.
x2, and it's not points. It's distance.
So you say the distances are in the no, but the task is to look at the labels and think about probability that the label is the same as the test label.
Yes. I just don't understand how to fix my solution.
Yeah, but to fix it, so you cannot ignore. You cannot only look at the distances because then you don't have the event. So you need to look at the points.
Yes.
And then if you say, so you need to bound probability of event, and you will split in many cases. For all sets of k distances, for all assignment of k distances, you create a condition, and then you take union bound over all the conditions.
In the sense, so I should make a big sum.
Yeah.
Over.
And then you have two cases. So either sum of so not all distances are at most d over 2 minus 1.
Yes.
But these cases have very small probability.
Yes, in this case I've done.
Yeah. And then there is other cases where they all at most, but when you condition on all these distances, then it's all these points are randomly selected within this distance.
Mhm.
So the rule is look to the look to all so when there is a tie, you look to the first points that go in the set.
Mhm.
And with this tie breaking, all the points become independent.
Okay.
So each point at given distance and at given place in the training set has uniform probability to be chosen. Because the learning algorithm doesn't look at the points, only at the distances.
Mhm.
So that's solution. It was difficult. It took me a long time to find it.
Yeah, but idea is to consider points, consider distances that are short and that are long. I'm done.
Yeah. Yeah, it's impressive. You have all maximal scores, but just the extra one and one quiz. Also, I think I will change the rule. I mean, if you need 3 points to have 10 out of 10 on final exam, I will give it right away. So then you don't need to come. So probably you will don't need to do the exam. But if you want, you can do it.
Here's some advantage points for students who study throughout the whole semester, have a rest during the exam.
Yeah.
That's nice.
Yeah.
Motivates them.
Well, it's not auto grading, but it's just like this quiz is for extra mark, and in the homework there is extra exercises. And then in the end it's rounded up. So if you have everything right in the course, then it will be, you will have no reason to go to the exam because you already have 10 out of 10. That's the plan. But I don't like auto grading if you have good homework and colloquium, because colloquium is just memorizing, and homework it's too easy to cheat. And then
Well, you have to do it consistently throughout the entire semester, so it takes something.
yeah, it's expensive.
Yes.
Yeah, if you want to cheat. Copy.